Hi, welcome to part 2 of the 3.3 wave systems tutorial. This will be all about interference and diffraction. So we have a red laser shining through a diffraction grating placed at the center of a semicircle screen. So the formula associated with diffraction gratings is this. So question A asks us, what does the term N wavelength represent when N and wavelength are combined? Okay, so this actually is the path difference. It is something you need to know and probably memorize. Now, I have a quick statement on what the path difference actually is, so you sort of understand it, and I can sketch it out for you. So, say your slits are here, for example. You've got your screen over here, and they both meet at the same point. So one's going to travel to here, the other one's going to travel here. Now they are not the same distance away from, so they will travel different distances that meet at the same point. That is what the path difference is. It's sort of weird, but as long as you can memorize this, that this always equals the path difference, you'll be good. It's only an achieved question, but it is quite an unfamiliar one, so just note this down if you have no idea what it meant before watching. Okay, I just wanted to clarify this first question a bit more because it might still be confusing. You see this, that little gap there? That's the difference in the distances of the light source. And that is what our inlander is, right? That's our path difference. That little extra distance you see there. And I've just scaled it up in that drawing. Hopefully that makes sense. Alright. Part B. The diffraction grating that was used has 200 lines per mm. Okay. That's important to know. The red laser has a wavelength of 638 nanometers. So again, we need to convert that to the right unit. Calculate the number of dots that are seen on the semicircular screen. Okay, so we're looking for the maximum amount of dots that will appear on the screen, right? So obviously it's going to be this formula here. Remember, if I draw my thing out, just pretend it's like the graph, and this is the circular screen here, CS. This formula here only gives us the amount of dots on each side of the central maxima, right? This is the central maxima, so that counts as one dot. This formula only gives us the amount of dots for each half. So we're going to need to find the number of n, whatever n is, and then multiply that by 2, and then plus 1. And that will give us the total amount of dots, okay? It's not just whatever we get for n is the total number of dots. You need to consider the central dot and the dots on the other side of the central dot. Okay, they said begin your answer by calculating the distance between the slits. So to do that, we're going to use this formula here. This formula is not on your formula sheet, so you do need to memorize it. I'll just put a little star next to it. You need to memorize it. So, it's going to be D equals 1. Now, N is the amount of lines per mm. Now, because it's per mm, we actually need to take that number and multiply it by 1,000, okay? To get the right number, because it's 200 lines per millimeter. That should give you an answer. If you put that into your calculator, you should get an answer of 5 times 10 to the negative 6. So it's going to be quite a small number. Okay? That is your separation distance between the slits. Now, for the maximum number of dots, we know the angle has to be its maximum. And for the angle to be its maximum, it has to be 90 degrees, right? That is the maximum angle that it could possibly be at. we know that sine 90 simplifies to 1, right? So our formula can actually simplify to n lambda equals d. So if we rearrange, n equals d divided by the wavelength, n equals 5 times 10 to the negative 6 divided by the 638 times 10 to the negative 6, because before it was in nanometers, and nanometers is 10 to the negative 6. So to make sure it's in meters, we just have to multiply it by 10 to the negative 6. And that should give you an answer of roughly 7.83 ... Now we cannot round up to 8. Remember, n has to be a whole number, so it can become 7. The reason why we cannot round up to 8 is we can't assume there's an extra dot, because that means we're exceeding the 90 degrees, which is just not possible. So you cannot ever round the number up. You always got to round it down. So therefore it's going to be 7. So the total amount of dots from the formula up here is going to be 7 times 2, because we're accounting for both halves, plus the dot in the middle, which is always going to be there, and that is going to be 15 dots. Okay, this is actually an excellence question. So usually part B is a merit question, but this one is quite tricky conceptually. So excellence, to get merit, you would have had to get this here, so that is enough for merit. And then to get achieved correct value for the separation distance. Okay, next question. Okay, part C. Mr. Smith uses the same red laser and shines it through 2 slits where the slits are of the same width as the diffraction grating, but the slits are further apart. The pattern on the screen is different compared to the pattern obtained in a diffraction grating. Okay, so describe the differences between the patterns, formed, and explain the reason for each difference. Alright, I'm going to write the answer down and then explain it. Okay, so the first point you need to talk about is the slit separation distance for 2 slits is far larger compared to a diffraction grating. Okay, now due to this formula here, if D is significantly larger, then that means the angle will be significantly less, right? Which means the dots are going to be closer together to the maximum, the central bright line, because the angle between them is less, right? So it covers less area. The second point you needed to have talked about is, since there's only 2 slits, there's less light actually diffracting, right? So to pass through, so the maximas, or actually it should be called the dots, are less bright, because there's not as many waves consistently, constructively interfering, okay? Compared to a diffraction grating where there's a lot more waves diffracting. The pattern is also less defined for 2 slits, and it will usually be fuzzy or gradually blend from the maxima to the minima. With the diffraction grating, the total interference from many slits result in more destructive interference, causing larger dark gaps, which makes the dots stand out much more clearly defined. So again, this is an excellence question. If you had all 3 points, you get an excellence. If you had any 1 point, if you justified any one really well, you'd get a merit. And then achieved as you talked about 1 like somewhat alright. Okay? So last question. We've got shines white light, okay, onto the diffraction grating. The pattern he observes has a central white region, and the other orders form complete spectra, which is a range of colors on either side of the central white region. Okay, Explain why white light forms a spectra with violet on the inside and red on the outside when passed through a diffraction grating. There's two ideas you need to know here, okay? And I'm going to write it down and talk about it. Okay, so white light is made of multiple colors, okay? It's not just white, okay? Each color has its own unique wavelength and frequency. You need to know that as well. Violet, or in the schedule they said blue, either's fine, has a shorter wavelength than red light, okay? Now we have to link it back to this idea of path difference again, unfortunately. We know that if it's got... So, sorry, I just got distracted by a call. The path difference is going to be less for violet because it's got a lower wavelength, which means it won't have as big of a path difference, compared to red light, which means it will form a maxima at a smaller angle, because remember this formula here, right? This bit here is the path difference, PD. If this is less, then this also has to be less, right? Because it has to balance each other out. So it forms a maxima at a smaller angle compared to the red light. If it's at a smaller angle, it means it will be closer to the maximum. You can see the angle of purple there compared to the angle of red, right? The angle of red is way bigger, right? That's why it's on the inside of the spectrum. The larger the angle, the more away it is, or the more outside it will be from the zero order central line. Okay, this is a merit question. If you have all 3 points, white light is made of multiple colors, each color has its own unique wavelength and frequency, and then you talk about the path difference. This is very important. You would get a merit. And then if you talked about either this part or this part, you get an achieved. And that is it for question 2. When everyone else finishes learning the Doppler effect, I will post a video on that closer to our end of topic test. Cheers! I hope you found it useful.